In this video and the next couple of videos, we will discuss how to calculate the change in enthalpy or the change in internal energy for the purposes of solving an energy balance problem if we don't have a table. So in the last couple of videos, I've talked about the steam table, table B8 and B9, and this is going to be the easiest and most direct way to do it. But what if we want to calculate the change in enthalpy, for example, of a species like benzene that does not have a table that is in the back of the book? How should we proceed? The first thing to recognize here is that enthalpy and internal energy are both examples of state functions. And this means that the quantity of the property only depends on the thermodynamic state of the species, not on the path taken to get there. So let's just say, for sake of argument, we had a chemical at state 1, and in the course of our chemical process, we know that it is going to state 2. All we need to know are the separate states. And I'll talk more about what that means in the next coming videos. But if we're changing more than one state variable at one time, then it becomes a little bit challenging to figure them all out at once. So we can use this property that it is a state function and construct a hypothetical process path. In other words, it doesn't matter if our chemical traverses directly from state 1 to state 2, or whether or not it goes through some alternative path. So let's say it goes to intermediate state 1.1, and then to state 1.2, and then even to state 1.3, and then finally to state 2. Both paths, the direct path and the around path, are going to have the same exact delta H. So we can calculate delta H for this process, or delta H for that process, delta H for this process, delta H for this process, and delta H for this process. And the fact that enthalpy is a state function means that this state is going to be equal to the sum of these four delta H's. So thinking about what are the potential process variables that depend on, or in other words, what does enthalpy depend on in terms of state variables? So I mentioned state variables. What does that actually mean? You'll talk more about state variables in your thermo class, which is coming up very soon. So what are the variables upon which H hat and U hat depend? Well, on the steam tables, we know that the steam tables were written for pressure and temperature. So those are two that we can write off the bat. We know that enthalpy and internal energy are going to depend upon pressure. We also know that they're going to depend upon temperature. Once again, I know that just from looking at the steam table and noticing that as pressure changes or as temperature changes, my H hat and U hat are in general changing. The third variable that H and U depend on is the phase of matter. And this is also something that we saw again in the steam table. When we transitioned from liquid water to steam, we saw a big change in H and U. So that tells us that whether or not the water is a liquid or a vapor will change what H or U is. A fourth state variable is the composition. This is the one that we'll talk the least about. And when I say composition, I'm talking about delta H of mixing. And in your chemistry class, you might have experienced when you're mixing chemicals, sometimes just the process of mixing something can make it very hot. So for example, I'm thinking of a particularly dangerous solution that I used to work with in my PhD called piranha solution. It's a mixture of hydrogen peroxide and sulfuric acid. When you mix those two chemicals together, there's a significant delta H of mixing that makes the solution get very, very hot. So there's no changes in pressure, temperature, or phase of matter, but just the process of mixing can elicit a change in H or U. And the final one that it depends on is the chemical species. And this is not something that we've seen before, and we won't revisit this until chapter 9. So here I'm talking about delta H of reaction. So if the actual species changes identities, different species have different chemical properties. So that's a different state of that species. Like I said, we're going to talk about 1, 2, 3, and 5. So that's pressure, temperature, phase of matter, and chemical species. Won't really get into delta H of mixing all too much, but you should be aware of its existence and that it can change what the enthalpy or internal energy changes are. So let's just start by going right down the line. In the rest of this video, we will talk about the first process variable, which is pressure, how to figure out what the change in internal energy or enthalpy is upon a change in pressure. So your book calls these type 1 processes, which I think is a little bit of strange notation, but we'll go with it. So type 1 is going to be referring to pressure changes. Maybe it's not your book. Maybe this is another book I'm thinking about that calls it type 1. Anyway, changes in pressure are the simplest that you can work out what the change in internal energy or enthalpy is. So there's different cases that we'll consider for changes in pressure. The first is for ideal gases. And remember what the main assumption of an ideal gas is, that an ideal gas has no interactions between molecules, no intermolecular forces or interactions. Therefore, if I change the pressure and I can still assume that it's an ideal gas, then the enthalpy and internal energy are not going to change at all. No intermolecular forces and reactions. So even upon a change in P, if I can still assume ideal, conditions, and I'm going to put an asterisk there. I'll explain that in a moment. We can say that the change in internal energy is equal to 0, and the change in enthalpy is also equal to 0. So this is the easiest one to remember. If I have an ideal gas and I can still assume ideal conditions, I'm not going to have a change in internal energy or an enthalpy because of the assumption that I've made. Now, the caveat to that, and the reason why I wrote an asterisk here, is because the ideal gas assumption may not hold. So for example, if I change pressure from 1 atmosphere, say, to 20 atmospheres or something, then I would have a change in internal energy or in enthalpy, but that's only because I don't have an ideal gas anymore. So that's something you may need to be mindful of. Now, of course, you can hand wave this and say, well, I'm going to assume an ideal gas no matter what. And that would be reasonably okay in this class only, but in future classes and in the rest of your career, that will not be an okay assumption. Okay, so let's say that you've changed the pressure large enough that you don't have an ideal gas anymore. For non-ideal gases now, how would you figure that out? And in this case, there is no equation or other method of doing it. The best that you can do is to consult a thermodynamic table or to find data. So for example, in the steam table, table B7, you can look up what the change in enthalpy or internal energy is upon changing the pressure of steam from one high pressure to another high pressure. And because steam is not an ideal gas at high pressures, you might notice that there is a change in internal energy or enthalpy. That doesn't follow any specific equation. So therefore, that's why you have to use a table or look it up in some way. And the final phase of matter that we'll consider is liquids and solids. And this one is also reasonably easy to remember. For liquids and solids, delta U hat is equal to 0. Or a better way to write it may be that it's not exactly equal to 0. I've just changed this to an approximately equal to sign. And this is, again, something that we've seen in the steam tables. If I change the pressure of liquid water, the internal energy does not change all that much. So the delta U is approximately equal to 0. And this is related to the fact that I'm assuming that the liquid or the solid is incompressible. That technically means that as the pressure changes, the specific volume or the density doesn't change, but it also extends to the idea that the internal energy won't change as well. So you might notice that we can assume 0 or close to 0 in a lot of cases. The only one that you cannot is when you're dealing with the internal energy of a liquid or a solid. And in that case, you can approximate it as equal to the density times delta P. So technically, it would be delta PV, and that is because H, remember, is equal to U plus PV, and therefore delta H hat is equal to delta U hat plus delta P V hat. And because we just said that delta U hat was 0, and we said that it's incompressible so that this V hat can be pulled outside of the delta, that's how we end up with this expression, where the change in enthalpy is equal to the specific volume times the change in pressure. So just as a note, make sure that you know that this has units of pressure. So I'll just write in parentheses here, watch out for units. And you may want to try a couple of unit conversions because delta H should be in units of energy. So that's kilojoules or something like that. And molar volume and pressure could be in other units, right? So it could be in atmospheres or something. So if I have a molar internal energy or kilojoules, let's say it's just joules per mole, and I wanted to work it out in the SI unit, I would need the specific molar volume in meters cubed per mole, and I would need the pressure in pascals. That's the only way that this unit conversion works. So you have to make sure that if you want your delta H in joules per mole, that your V hat is in meters cubed per mole and your pressure change is in pascals. And you should see that unless your pressure change is very large, your delta H upon a change in pressure is going to be pretty small. So there's a chance that you may be able to neglect it anyway. But just keep this in mind. I would recommend that you keep this table handy in your notes. This is useful to refer to if you ever need to perform a change in pressure at constant temperature phase composition with no reaction. You can just simply look up what the change in internal energy or enthalpy is. That'll do it for this video. See you in the next video.